Okay, so welcome to the lectures of our System Dynamics and Control course. So last lecture we discussed the derivation of power unit equations yesterday, and we are deriving in fact all the equations in power unit, and we have seen that the voltage equations we have derived, and also the electromagnetic torque in power unit we have derived. And today we'll see how to derive the power unit equations of Flux linkage equations. Then finally we'll see all the algebraic and differential equations in power unit. Okay, let us go ahead. So just whatever we have covered little bit, we can see here the electromagnetic torque equation. We have seen that this S will be in the dq frame of reference. S will be equal to 3 by 2 Vd Id plus Vq Iq plus twice of Vu Io, right? And then after substituting the equation for Vd, Vq and Vo in this equation, and making just few manipulations, we can find the equation for S in terms of three components. One component will give us the rate of change of flux linkage, that is rate of change of magnetic energy in the stator coil. And the second component will give us power transferred over the air gap. And third component is the stator copper loss. So all these three, out of these three components, that component which is actually the power transferred over air gap, that will be responsible for the electromagnetic torque development. So therefore we'll consider that component only, and we'll derive the torque equation that will be 3 by 2 p by 2 into lambda d iq plus minus lambda q id Newton meter. This is in Newton meter, and where this p is actually, in fact, this p is your number of poles. Okay. Then in order to convert to this power unit system, we need to find the base torque. So base torque we have derived, and that is nothing but 3 by 2 into p by 2 psi of dq base and I of dq base. Now in order to find the power unit quantity, we need to divide the actual torque by the base torque, and after dividing we found the equation is nothing but it is psi d iq minus psi q id. Okay, so this is your, up to this we have discussed yesterday. And now we'll discuss today the stator and rotor flux linkage equations in power unit. So stator flux linkage equations we have already seen, that is lambda d will be equal to LLS plus LMD. This is nothing but it is LD. So LD I can write LLS plus LSD, right? I can write LLS plus LMD into ID plus LSFD IFD plus LS1D into I1D. Similarly, your lambda FD I can write 3 by 2. Already we have derived this. LSFD ID plus LFD FD IFD plus LFD 1D I1D. Then your lambda 1D, similarly, we have seen these equations already. And we know that ID in power unit, that is capital ID, is nothing but is equal to small ID by IDQ base, and IFD similarly other power unit quantities IFD and I1D in power unit we can express in terms of this. Then I can now divide the lambda dQ base across the all these three equations. Like for the lambda d equation, I can divide lambda dq base both right hand side and left hand side. Again, I will divide the lambda fd base in the lambda fd equation. So you should remember this lambda FD and lambda 1D is associated with rotor, right? And this is associated with stator quantity. Okay. So therefore, so we are dividing lambda FD base in lambda FD equation, and again lambda 1D base in the lambda 1D equation, right? Now just wait, we'll take the symbols of the power unit expression. Now your lambda D in power unit will become, that is flux linkage in D axis, and the stator side in power unit will become psi D. Okay, so psi D will be equal to nothing but the same, we'll see, because lambda dq base will be nothing but v dq base by omega base. So now it will become minus omega base LLS plus LMD into ID base. So ID, small ID, that is the actual ID, I can write the per unit quantity into base quantity, right? So similarly for IFD also we have written here IFD into IFD and base, and I1D I can similarly write I1D into I1D base, right? Then psi FD I can write a similar way, whatever way we have defined in the above side equation, right? In a similar fashion we have written, so lambda FD base will be equal to VFD base by omega base. Okay. And similarly psi 1D equation I can write, that will be minus 3 by 2, because psi 1D lambda 1D base will be nothing but V1D base by omega base. So therefore omega base will go to the numerator, so it will become omega base LS1D IDQ base by V1D base. Similarly, all these terms, second and third terms, can be written. So I hope you understood these equations. So now I will go ahead. Similarly, I can write, because already we have considered IFD base is equal to LMD by LSFD into IDQ base. And VFD base, of course, we have seen, we have derived it, that is 3 by 2 LSFD by LMD into VDQ base. And I1D base, similarly, we have found, that is LMD by LS1D into IDQ base, and V1D base also we have found this. Now if we substitute these quantities, now what expression we'll get? Okay, before substituting this, let us find the per unit reactance quantities. So your XLS, whatever here it is mentioned, like omega base into LLS will become XLS, right? So now we'll define these quantities in per unit. So your XLS in per unit will be XLS by ZDQ base. So that will be omega base LLS by ZDQ base. And that will be omega base LLS IDQ base by VDQ base. Similarly, XMD, I can write this expression, right? So all these expressions we can substitute in the flux linkage equation. Similarly, XMQ also I can write like this. Similarly, XFD I can write like this, right? That is in terms of omega, L, IFD base, VFD base, right? Similarly, XLS also we have written in omega, LS quantity, then IDQO, then VDQ, right? Similarly, I can define X1D also. X1D also written in terms of omega base, L1D 1D, and I1D base by V1D. Now I can substitute, instead of these quantities, I can substitute these per unit reactance values like XLS, XMD, XMQ, XFD, and X1D. I can substitute this. So now this expression here, we have many terms which we can substitute through the reactance. Now substituting this, we'll get, okay, now X1Q also is there, X1Q and X2Q, okay. So these are also can be expressed in terms of omega and inductance quantities and the corresponding base quantities. And similarly, xfd1d and x1q2q. Okay, so these are the expressions where we can substitute these reactance values, reactance quantities, right? Now just substituting. Okay, so before we move, uh, we can have q-axis flux linkage equations. Similarly, in similar way, we can write the q-axis flux linkage equations: psi q, psi 1q, psi 2q, right? In the same fashion, we can write, right? So just a little bit manipulation, and we can write these equations. Again, we can define the I1q base, I2q base, V1q base, and V2q base, right? Already these quantities are defined. Just for your remembrance, I'm showing this. Now, again, XLS, XMD, XMQ, XFD, X1D, X1Q, X2Q. Again, this will be very useful to substitute in psi q and psi 1q, psi 2q equations, right? So now we can, and we must remember this, that this psi q is in fact associated with the stator quantity. Okay, this is your associated with stator. Okay, and these two equations are associated with rotor. Okay. Okay, so now if we'll substitute these expressions in terms of the reactance, per unit reactance quantities, then we'll get final equations. ID will become equal to XD into ID plus XMD IFD. These are all in per unit. The side is in per unit, XD is in per unit, ID is in per unit, plus XMD IFD plus XMD I1D. Okay. Similarly, your XIFD equation can be written as XMD into minus ID plus XFD into IFD into KD XMD I1D. So what is this KD? KD is a constant which is defined as LFD1D by LMD, and KQ also is defined as L1Q2Q by LMQ. So this similarly, your psi 1D also can be written as XMD minus ID plus KD. KD is this, and XMD IFD plus X1D I1D. Similarly, your psi q, I can write XQ minus IQ plus XMQ I1Q plus XMQ into I2Q. Similarly, psi 1q and psi 2q. Psi 1q I can write XMQ minus IQ plus X1q IQ, I1q plus XQ, XMQ I2Q. Similarly, psi 2q. So all these flux linkage equations, now it is expressed in per unit. This is in per unit. All these equations are in per unit. Okay. So now finally we got these equations. So these are algebraic equations, right? Psi d, psi fd, psi 1d, psi q, psi 1q, psi 2q, right? And now we have these voltage equations. If we'll summarize whatever per unit equations we have derived, that we derived VD, VQ, and VO. These are the stator voltage equations in DQ of frame of reference, and then voltage rotor voltage equations, that is VFD, V1D, V1Q, and V2Q, right? Now these equations, if you'll see, these are differential equations, right? And next we have derived the Flux linkage equations in per unit, that is psi d, psi fd, and psi 1d, right? These are algebraic equations. Then in q-axis flux linkage equations, psi q, psi 1q, and psi 2q. Here if you'll see, psi d and psi q, they are associated with stator flux linkage equations corresponding to d-axis and q-axis. And here psi fd, psi 1d, here the flux linkage equation of the rotor corresponding to the d-axis, And psi1q and psi2q, they are also their q-axis flux linkage equations corresponding to your damper windings 1q, 1, 2q, right? Okay. So now these are the equations, per unit equations. We'll use again to modify these equations. We'll find the constants, the parameters of the machine, right? And using that, we can express the algebraic equations as per the industry standard. Okay, that is our objective. So we need to model the machine so that it should be the equation should be in terms of the parameters of the machines, which is in fact as per the industry standard. Okay, so we'll go ahead. So now we'll talk about synchronous machine parameters, which will be very useful to express these equations, right? We'll see now. So synchronous machine parameters. So it is customary to represent the voltage equations and Flux linkage equations in terms of subtransient and transient reactances, open circuit, subtransient and transient time constants, right? And parameters of the industry grade synchronous generators are given in terms of above parameters. So then we'll see how the subtransient and transient reactances we can derive, right? So first let us consider, suppose a voltage is applied at the stator terminals with all circuits short circuited such that only the current ID flows. Then immediately after the voltage is applied at t equal to 0 plus, what will happen? The flux linkage psi FD and psi 1D will become 0. And psi 1D will be 0, right? It is not immediately, it will not be some value, right? So therefore your psi D, I can write psi D equation which we have derived already, that is xd into minus id plus xmd ifd xmd I1d. Then your psi fd equation, which is nothing but xmd id minus id plus xfd ifd plus xmd I1d. But initially because it is 0, so therefore I will write it is equal to 0, right? And then your psi 1d also will become 0. So it is nothing but equal to xmd minus id plus xmd ifd plus x1d I1d. Already we know these equations, right? Now xfd I know, that is if I'll segregate this, it will be xlfd, that is the leakage reactance plus mutual reactance, that is xmd, right? Similarly x1d I can write in a segregated form, that is xl1d plus xmd. xl1d is nothing but this is the leakage reactance and xmd is your mutual reactance, right? Now if we'll considering these two equations, if I will just eliminate I1d from both the equations, I can find the expression for IFD in terms of ID, right? Similarly, if I'll eliminate IFD from these two equations, I can write I1D in terms of ID, right? Okay, just see here. Just eliminating, you can also do this in your home, you can try it in your hostel. So just by eliminating I1D from these two equations, I can find IFD in terms of ID. You can see here ID and other reactance values, right? So similarly, I can eliminate IFD from these two equations and I can write I1D in terms of ID. This is what we can see, I1D in terms of ID, right? Now if I'll substitute these two equations, IFD equations and I1D equations in the first equation of psi d. Okay, first equation of psi d. Now my equation will be, whole equation will be in terms of, so psi d I can represent in terms of ID only, because there will be no term IFD and I1D, right? Now from there I can find the transient and subtransient reactances, right? Now we can see here, if I'll substitute IFD and I1D in this equation, what I'll find. So now after substituting and manipulating, just little manipulation we need to do. After doing that, I will get psi d in terms of ID. Okay, here. Psi d in terms of ID, right? So now it is all power unit reactances. Xt minus of xt minus xmd square xlfd plus xl1d xmd xlfd plus xmd xl1d plus xlfd xl1d. So now I can just little manipulation I'll do. I'll substitute xt equal to xls plus xmd. Okay, and just substituting this xt equal to xls plus xmd and little bit manipulation if I'll do, then it will become xls plus xmd xlfd xl1d divided by xmd xlfd plus xmd xl1d. The denominator will remain same. Only change is the numerator, and here the term will become xls, right? Now if I'll divide this numerator across the denominator, right, then it will become 1 by xmd plus 1 by xlfd plus 1 by xl1d. Okay, and that is added to xls into id, right? Now this whole term, if I'll represent through a parameter that is known as xd double dash, right? Okay. Xd double dash, then this xd double dash will be known as the synchronous subtransient reactance. Dx is subtransient reactance. Okay, please mute yourself. So your psi d, I can write minus xd double dash id, right? Is id. Dx is flux linkage. So your xd double dash is nothing but this is your expression for xd double dash. So your xd double dash will become equal to xls plus 1 by 1 upon xmd plus 1 upon xlfd plus 1 upon xl1d. Okay. Similarly, if in the q-axis flux linkage equation, if I'll analyze and just I will manipulate it, q-axis flux linkage equations, all the q-axis flux linkage equations, I will find the subtransient reactance xq double dash as this, right? xls plus 1 by 1 upon xmq plus 1 by 1 upon xl1q plus 1 by xl2q. So these are the two expressions for subtransient reactance, right? So okay, so we till now we derived the subtransient reactances, and using these subtransient reactances we can write the equations, all the algebraic equations. So we'll derive it. Subtransient reactance and also the time constants. Subtransient, transient reactance, then your open circuit time constants. Okay, so we'll do it. So for deriving the equations for transient reactances, the same logic can be applied with an additional assumption that the damper winding transients settle down faster as compared to the field winding transients. Hence, I1D can be assumed to be 0. Okay. So assuming I1D 0, because the assumption is taken here that the damper winding transients settle down faster as compared to the field winding transients. So it will be assumed that your damper winding transients are settled down and the field winding transients are existing. Under that condition, we'll find the transient reactance. But here in case of subtransient reactance, we assume that the damper winding transients are there and field winding transients are still there. Okay. So okay, we'll stop here, and the next class we'll discuss more how to derive the transient reactance and the time constants. Okay, so we'll do it in the next class. Okay, so thank you very much.